this is a talk that's going to be going over some stuff that's coming to Rust. Some of it has already landed in beta, and okay, this is already a problem. I can't let people in. Chester isn't here. But yeah, anyway, we're going to be covering some new features coming to Rust. So there's a lot of stuff that hasn't been finalized yet regarding pointer provenance and the associated APIs. So do take everything that's said here with a grain of salt. But at any rate, let's just jump into things. So yeah, first off, we're going to start really simple. We're going to talk about what a pointer is. And from there, we're going to talk a little bit about what the meaning of provenance is. And then finally, I'm going to be going over the differences between the strict provenance APIs and exposed provenance. So yeah, let's dive into what a pointer is. So typically, when I talk about pointers, I usually go to this diagram here, where this is kind of what memory looks like from like a very high level view. You got your addresses here, and you've got values that can be stored at each address. And so, like for example, you might have a statement like this in Rust, where you create a new variable I, you set it to the value 4, and then that gets stored at some address here, right? And we can see that we have another value here. This one is actually a pointer, so this is how we can construct a pointer. We can say let ptr equal this %I. We'll give it a type of star const u32. So u32 is the unsigned 32-bit integer. So this is just a pointer to a unsigned 32-bit integer. And what you'll notice is that the value here is just another integer, right? It's an integer that happens to be the address of another value. Let me just let someone in here. Oh, okay, I guess we're fine.
I let them in.
Oh, okay, you're back. Okay, cool. Thank you. So yeah, that's basically pointers in a nutshell. A pointer is basically a value that happens to be the address of a different value, or at least that's what you would think. That's kind of like the beginner's definition. So we're gonna see how we expand upon that in a bit. So first of all, I want to talk a little bit about raw pointers in Rust. So I've got a little playground here to sort of demonstrate the concept. So if you're new to Rust, essentially, this is how you would define a variable. You use the let keyword. You give the variable name followed by a colon, then the type name. So this is a u32, so we can give it an integer value like this. And optionally, you can also include this mute. Depends on whether or not you want to be able to mutate this variable binding, right? If you want to set this to 2 instead, or 3, or some other integer, then you need this. So here's how you would create a pointer, a raw pointer in Rust. I want to make very sure to distinguish. So when you're creating a raw pointer in Rust, use this ampersand syntax for your variable name. So it's very similar to C if you're used to that. And here's the pointer type. It's a star const u32. This const means that this pointer is read-only. So we can't mutate the content behind that pointer. If we want to read from the pointer, then we can use this dereference operator. So just put a star in front of the pointer's name and then wrap it in this unsafe block. This is necessary because in Rust, we want everything to be safe by default. So if you want to opt out of that safety and do something potentially dangerous, like dereferencing a raw pointer, then you have to use this unsafe block. I don't want to dwell too much on unsafe today. So yeah, here's the read and write pointer. So again, it's similar to the star const pointer, except we use star mute. Instead of using just an ampersand, we use ampersand mute. And here, if we want to actually set the value that this pointer is pointing to a new value, you can actually do that. You can just use the dereferencing operator on the left-hand side of the assignment operator. Again, you have to use unsafe in order to do this. And if we want to read that value, then of course we have to also, again, use unsafe. And so as you can see, like this first line will print 1 because that's what the value was here that this is pointing to. And here we set the value to 2. So now when we print the value pointing to by pointer mute, we get a 2. So why do we care about raw pointers in Rust? So, typically, right, if we're writing Rust, we're going to use something else called references. But there are times when you actually will want to use raw pointers. So raw pointers in Rust are used in contexts where you have to do manual memory management. So for example, like what I have to do at work is we have to do a lot of FFI. So we're having Rust code talk to C code or Java code or any other language that communicates to other languages through like a C ABI, right? So in those cases, you're kind of working at a low enough level where you actually do need to worry about pointers because you're potentially interacting with a language that can do practically anything, right? If you're talking to C, C can dereference pointers willy-nilly. So that's a primary use case for raw pointers in Rust. And again, I want to stress that you do require the unsafe keyword whenever you want to dereference a raw pointer in Rust. And that is in contrast to Rust's references. So Rust references are a little bit different. They're pretty much, so they're meant to always be safe to dereference. And this is kind of one of the bigger selling points of Rust for a lot of people is, you don't have to do this runtime memory management kind of thing, you don't have to have like a garbage collector that runs at runtime. You also don't have to like manually manage memory in order to stay safe. So you have a little bit more control there, but you don't run into memory corruption issues. So here's how Rust's references work. So we have a few functions here. We're going to start with borrow. So what borrow does is it borrows a value. So Rust has this concept of borrowing. It's very similar to like C++ move semantics if you're familiar with that at all. But yeah, when we borrow a value, we basically take a reference to it. So that's what this ampersand U32 is. It's very similar to the star const U32. It's just that instead of star const, we're putting ampersand instead. And in this case, we're borrowing two different values. We're borrowing an x and a y. These are both references to 32-bit integers, and then we just print them like so. And if we want to run this code down here, right, we can see that we create a variable x. We're marking it as mutable for later, but we pass it to borrow by reference. So in order to pass something by reference, again, just like when you create a pointer, you have to use this ampersand syntax. So we're going to pass in two references to x, and so we just get 1 and 1. Now, if we look at this bit of code here, so here we are passing two mutable references to x. So again, this is sort of like the star mute case that I showed earlier, to this borrow mute method, which basically does kind of the same thing that borrow does, except it mutates the value pointed to by these two references. It sets them to 2 and 4. But what you'll notice here is that if we try to build this code, it's going to complain about that. And that's Rust's borrow checker kicking in. So essentially, this creates what Rust would consider an aliasing bug, right? Where you have two different references to the same region of memory, and they both have write access. So potentially, you might run into some bug where you expected that these are two different references, but the caller passed in two of the same reference. So you get funny values coming back out. So that's disallowed by default. Here we're calling borrow mute again, but this time we're actually going to give it two different references, and this is totally okay because, again, we're pointing to two different regions of memory, right? This is a reference to X, this is a reference to Y. And so this is totally okay. You can kind of see, based on that reasoning, why this might not be okay. So we're doing a mixed borrow, so we're taking an immutable reference and a mutable reference. And in this case, if we pass an immutable reference and a mutable reference to the same object, then it's not going to compile because this reference is supposed to be read only. So you expect that the value should always be the same every time you read from it. But if this reference happens to point to the same region of memory and overwrites that value, then suddenly that contract is broken. So that's why this isn't allowed. But of course, if we look at this code down here, because we're passing a mutable reference to Y instead of X, that is allowed. So that's kind of a quick rundown of pointers and references. This is how Rust, keeps you safe. Typically, this is what you would normally be working with. But if you're like me and you have to do FFI on the job pretty regularly, then you have to work with the raw pointers. So we need to think a little bit harder when we're trying to work with raw pointers about how to safely dereference them. And so there's actually an entire document explaining, how all this works. So there's a bunch of precise rules here, but again, not everything is fully determined, as you can see here. But yeah, they do have some idea of how this is supposed to work. And one concept that you will see that pops up a lot in talking about dereferencing raw pointers is this notion of provenance. So this is an excerpt from that page where they talk about how the provenance of a pointer is used to determine which allocated object it's derived from. So let's talk about what pointers actually are. So I told you that a pointer is basically just an integer that happens to be the address of another value, and that's only half right. So pointers are represented by the usize data type. This is an unsigned integer data type. So it is technically just an integer, but pointers actually have another component to them that we don't generally talk about too much, which is their provenance. So in reality, whenever you're trying to convert from a pointer to an integer, that's actually typically a lossy operation because you're just getting an integer back and you're losing the provenance of that pointer. Now, there are some exceptions to that, such as, if you create a pointer using this without provenance function, right? So this just takes an integer address and then it gives you back a pointer. And like it says here, it creates a pointer with no provenance. However, when you have a pointer with no provenance like this, you're only allowed to use it for zero-sized memory accesses if suitably aligned. So basically, you can't actually read any bytes of memory using this pointer. So that is something to look out for. But yeah, in general, if you have a pointer and you want to be able to actually read data from it, then you're going to have some notion of provenance associated with that pointer. So now that we've kind of established the importance of provenance, we need to talk a little bit about what provenance actually is. So the dictionary definition of provenance basically says that it's the chronology of the ownership, custody, or location of a historical object, or in other words, it's basically just a historical record of an object, like who owned it, where did that object go, for how long was it owned, that kind of thing. And so that also applies here in Rust when we look at Rust's definition of provenance. So just to reiterate, a pointer consists of two components. It consists of an address, right? That's the integer portion, but it also consists of a provenance. And provenance is defined as containing three components. So there's a spatial component, there's a temporal component, and also a mutability component. And what's interesting about the mutability component is that it interacts with the other two components. So for instance, with regards to the spatial component, right, maybe a pointer is only allowed to read and write from like a certain subset of addresses that normally it would be allowed to access. And same with temporal, right? Maybe you're only allowed to write to certain addresses at certain times. So you're not necessarily always going to have the ability to mutate, even though you have proper access to that, or you might have access to write to it at certain points in time. So that's a little bit of provenance. We're going to jump into some code examples in a second just to motivate this a little bit more. But before we do that, I want to talk very briefly about what strict provenance is. So strict provenance is a set of APIs that is being added to Rust. I think it's in like it's being added to the standard library. I think it's in beta right now. I'm not 100%, but it's essentially designed to make working with provenance more explicit. So, for instance, one of the big functions that they like to point out is this with address function, which is what you would use for integer to pointer conversions. So if you remember earlier, I was talking about how a pointer to an integer conversion is a lossy conversion, right? But an integer to a pointer conversion is a little bit different because now you're going from less information, just an integer, to more information, an integer and a provenance. So you're not really allowed, at least you're not supposed to be able to just take some integer and then cast it to a pointer. And that's what strict provenance disallows. If you want to do that, you have to use something like with address. And with address doesn't exactly just do just that. So this is the signature for with address. Self here is actually a pointer, and this self is a new pointer. So what's actually happening is instead of just taking an address and giving you back a pointer, you have to also pass in another pointer. So this pointer's provenance is going to be used to determine the provenance of this new pointer. So it's not really like an integer to pointer cast. A little bit of extra information is required to make that work. So without further ado, we're going to jump into some code examples here. So the first example I want to show off is this address to pointer function. Just to quickly jump down here, this is what our main function looks like. So we're just calling address to pointer, and the rest of this code is commented out for now. There's a good reason for that. We'll see that in a moment. But essentially, this is the integer to pointer casting that I was saying you're not allowed to do, or you shouldn't be allowed to do it. So if we run this code, you'll see that it gives us a few warnings here, but it's not actually going to complain about this at all. It's like, oh yeah, this is totally cool. And what this code is essentially doing is it's just taking an arbitrary integer, in this case 0, and it's turning it into a pointer or an address. So if we wanted to dereference that, we'd just be pointing at memory address 0, whatever that is. We don't know what's actually there, and of course, that's probably pretty dangerous. So what we can do instead of just running this code is we can actually come over here to these tools, and we can run something called Miri. So what Miri does is it tries to detect undefined behavior in your code. But the way that Miri works is it's not like the compiler. It doesn't do a static analysis. It's a dynamic analysis tool, so it actually needs to execute your code in order to detect these cases. It's similar to like Valgrind, if you're familiar with that. And so now if we come down here, we're still getting only warnings. However, we get a very interesting warning here, which says that we're doing an integer to pointer cast. And it says that that's not a good thing. We shouldn't be doing that. So it's telling us that we should be using the strict provenance APIs if we want to do this sort of thing. If we don't want this to just be a warning, you can also set this Miri flag here for strict provenance. And this is something that I would recommend if you're working with raw pointers and you want to make sure your code is safe. You want to make sure that Miri is catching all the bugs. You want to put this in like your CI process, right? You probably want to enable this flag so that you're using these strict provenance APIs, because otherwise this code right here, this is just going to come out as a warning in Miri. So yeah, that's the case that we want to be careful of. Next, I'm going to talk about a little function called wrapping offset. So there's documentation for it here. If you want to go check that out. And that's where this example comes from as well. And essentially, what this code is doing is it's creating an array here of 5 bytes. We're using U8 to denote that this is a byte. And then we turn that array into a pointer using as pointer. Then we define a step size and an endpoint. So this end rounded up is basically what we're going to be iterating through this array until. So we're choosing pointer.wrapping offset 6. And what this does is it gives us a new pointer that points to the address that PTR is pointing to plus 6. So essentially, it's doing pointer arithmetic for us. So we're going to see it go from index 0, 1, 2, 3, 4, 5, and then 6. 2 elements past the end of the array here. And so what we do here is we create a new output variable. This is just a string. This is an empty string. And while our original pointer is not equal to this endpoint pointer, remember that was 2 past the end of the array, right? Then we're going to append the byte that pointer is pointing to the string, and then we're going to use wrapping offset to increment pointer by the step size, which is 2. So that's why we see this output of 1, 3, 5, right? We're going from 1, step size of 2 to 3, step size of 2 to 5, and then step size of 2 to 2 elements past the end of the array. And then these pointers will become equal, and then the loop terminates. So that's a little bit about how wrapping offset works, but of course, it's not that simple. There's a bit of a catch to it. So here's where provenance sort of rears its ugly head, so to speak. So this is the provenance example that I have here. I'm going to actually move that back in. So if we want to run this code, yeah, we see that there's nothing wrong here, at least from what we can tell. Right? It says it's going to print out the value. There's no big scary error messages. But as we're going to find out, this code actually has some undefined behavior in it. So let's see what this code is actually doing. We're creating 2 arrays of bytes with 5 bytes each. So this array has values 1 through 5. This one has values 6 through 10. And then we're going to create 2 pointers this time instead of just 1. So we got pointer 1 and pointer 2. And now we're going to call wrapping offset in a very peculiar way. So we're calling it on pointer 1. So pointer 1 points to the first element of data 1. And we're going to give it an offset of pointer 2 minus pointer 1. And so we can kind of substitute like concrete addresses here to kind of gain an intuition for what this is doing. Like let's say that this is address 0 and this is address 5, right? Then if we're taking pointer 2, which is 5, minus pointer 1, which is 0, we just get back 5. And so essentially, what we're getting out of this wrapping offset call is a pointer to address 5, or the first element of data 2, which is equivalent to pointer 2. So that's what pointer 3 is. Pointer 3 is equal to pointer 2. However, and this is something that the compiler didn't actually catch for us, but if we were to run this through Miri instead, like so, you'll see that it actually says that this is undefined behavior. It says that this memory access failed. We got something that was beyond the end of the allocation of size 5 bytes. So this is where provenance actually kicks in. So despite the fact that pointer 3 is a new pointer that points to a valid memory address, which is the same address that pointer 2 is pointing to, because we called wrapping offset on pointer 1, the provenance of pointer 1 is, I guess, it's passed over to pointer 3. So pointer 3 inherits pointer 1's provenance. So remember, a provenance consists of a spatial component, among other things. And that spatial component says that, hey, pointer 1 is only allowed to point to these 5 bytes. You're not allowed to point to anything else. You have to be within the bounds of this array. And so when we create pointer 3 with the same provenance as pointer 1, Miri can actually recognize that, hey, you're reading from this other array. You're reading from data 2. That's not in the provenance. That's not in the spatial component of pointer 1. So this is now considered undefined behavior. And if you're wondering, like, how do I know? Like, how do I know that the provenance is being inherited and stuff like that? Well, it's actually in the documentation here. So if you go to this page, you can actually see that they talk a little bit about how this resulting pointer remembers the allocated object that self points to. So this is sort of like an informal definition of provenance. So that's essentially how provenance plays into memory safety and undefined behavior. So it's actually a little bit it's a little bit tricky to wrap your head around if you're not using stuff like Miri to double check your work. So that's strict provenance. We talked about how you're not allowed to do integer to pointer casting. You have to use with address, or you can use another function like wrapping offset, which will do similar sorts of things, right? So if we exit the world of strict provenance, we enter what is called exposed provenance. And in exposed provenance, of course, you're allowed to actually do integer to pointer casting. So this is useful in some bare metal situations where you have to synthesize pointers without passing in some other previous pointer to leech provenance from. But of course, this is a lot less safe. There's less solid semantics around this, and it's unclear right now whether there's a satisfying unambiguous semantics that can be defined for this, at least for now. So this is sort of a work in progress, but essentially, if you want to stay safe, just try to avoid exposed provenance if you can. Like, obviously, there are some use cases where you will have to use it, but like, for instance, for our use case where we're just doing a bit of FFI, we're just writing wrappers around a client, that kind of thing is pretty doable without needing to use exposed provenance. So yeah, just to wrap things up here, here's some key takeaways. Pointers are not just integer addresses. They also have a provenance. We saw how that works with wrapping offset, where pointer 3, somehow, for some reason, even though it's pointing to a valid memory address, is still considered, it's pointing somewhere where it shouldn't have access to, and so it's triggering that UV warning or that UV error from Miri. Integer to pointer casts are not allowed by strict provenance, but they are allowed in exposed provenance. We also have this Miri flag. This is something that you'll probably want to set in your own projects if you want to use strict provenance, if you want to actually enforce that. Very useful for CI again. And last but not least, I just want to stress that Miri is a dynamic analysis tool. It's not going to check any code statically. So if you want to detect undefined behavior using Miri, you must make sure that your tests actually have proper coverage before you run Miri. So yeah, that's pretty much the entire thing. So there's some further reading here if you want. You can read about pointers here in the pointer module page, the beta documentation. I showed this off a little bit earlier, but there's a lot more to be said here. I didn't want to go over all of it because it's quite frankly a lot. But yeah, that's pretty much it. So does anybody have any questions or comments?
Yeah, I've got a question. So what does pointer provenance let us do that we can't do without it?
That's a good question. So I believe that it allows us to use pointers in. It allows us to do things like pointer arithmetic. I guess safely, for some subset of safe. But you still have to use unsafe because you're still working with raw pointers, right? Like the way that Rust handles this isn't really the best. There are other languages that have stronger guarantees around this kind of thing. Like if you look at the like research languages like ATS2, for example, they have found a way to, or at least rumor has it that they found a way to actually do pointer arithmetic safely and have it actually be enforced by the type system at compile time because they're using a more powerful type system. They're using dependent types, which is something that Rust doesn't have.
Yeah.
So this is basically trying to recover some of that power, being able to like reason about things like pointer arithmetic, giving you the power to do things that are a little bit more tricky to verify through regular references, using raw pointers, of course. And that's why you have to use Miri to do the dynamic analysis, because that information isn't exposed in the type system. It's not statically checkable.
Gotcha.
Anybody else?
Sorry, I had joined late, but I just wanted to ask if Providence is basically like an invariant that needs to hold for the raw pointer. So we're just trying to keep that invariant true when we're doing arithmetic.
Yeah, in essence, it kind of is. So provenance is basically three components. There's like a spatial component, which is the set of addresses that your pointer is allowed to point to or access memory from. There's the temporal component, which is talking about like the time span in which you're allowed to access those memory addresses. And then there's the mutability component, which is whether or not you're allowed to read and write from certain addresses at certain times. So yeah, essentially it is just like an invariant. It's something that, again, like I said, it's something that can be checked statically if you have the proper tooling, if your language supports it. But Rust doesn't really do that, so it uses Miri to do that instead. Anybody else? Going once. Going twice. Okay. Cool. So with that, thank you all for listening to my talk. We've got a bit of time for free discussion. I actually have a question that I wanted to go over in case anyone has used Tokyo. So this is a question that I've got coming in from a coworker. I don't know if anyone has worked with Tokyo streams at all, but apparently he's been running into issues trying to call the right vectored method on streams in Tokyo. And apparently he needs to add some kind of sleep delay in order to get to actually get to the server. When he uses this call, I don't know if anyone has ever encountered this issue before. Very specific.
I'm sorry, I didn't quite get you. Which method is he trying to call on a stream?
Right vectored.
No, I've never used that.
And I can also paste the method here.
Right vectored.
Have you tried asking on the Tokyo Discord?
No, we haven't done that yet.
Yeah, that would probably be my next step.
Okay, interesting.
I've also had good luck just sort of spelunking through old Tokyo issues. It's possible someone else hit this in the past.
Just like on their GitHub?
Yeah.
Okay. Yeah, I haven't really looked into it too much. It's just something that came up. I've never worked with this before, so I just didn't really, I didn't have any idea. I didn't have any context for this. Well, if anyone else wants to talk about something like the projects, or if they have any questions about Rust or something else, then now's a good time to talk. Anybody working on any interesting projects? No? I've been playing around with Vulkan recently, trying to figure out how to use Vulkan in Rust. Not really too sure if I want to actually commit to it though, because it seems like it's a much lower level API than OpenGL, and I don't know. It sounded to me like OpenGL was being deprecated, at least on like Mac OS, but yeah, I'm not really sure. I'm not really sure what the story is behind that. Probably need to dig into that a little bit more. But it sounded like they were trying to replace it with either like, was it Metal? I think Metal and Vulkan are like the new graphics libraries that are being used to replace that.
Huh. Last time I dealt with OpenGL was a few years ago, and it seemed to be going strong, though I was working on Linux at the time, not Mac OS.
Maybe, yeah, that might be a Mac specific thing then.
There are a lot of Mac specific things. That's actually why I gave up on it.
Yeah, I remember everyone being like, "Oh yeah, Mac is like the best development platform. You should always just use a Mac and stuff." For like the longest time for so many years, and I don't know. Eventually, I got a Mac because I had to for work, and then I don't know, just doesn't seem as great as everybody was saying it was.
It let's see. I got on the Mac back in 2014, and it was quite nice, and it was just a beautiful piece of machinery as well.
Yeah, I
But
think the
over the
hardware
years,
is the biggest part.
yeah, yeah. But every release, they lock it down more and more and more. And after one OS update, I was unable to run GDB anymore because I've done a lot of C++ development in the past and C development, and that's when I kind of, what can I do? So yeah, I moved to Linux laptops, and to Rustam's comment, I just cringe every time I listen to music or watch video on a different platform. But you can actually develop on it. Yeah.
Nice. Yeah, I semi recently got like a Linux desktop machine. I'm actually running NixOS on it because I was interested in trying that out. It's kind of regretted in some ways, but I've kind of gotten used to it now, so it's not the worst thing in the world.
I run Arch on my desktop, and I've been pretty happy with it.
Okay, cool. Yeah, I've been hearing some rumblings about how apparently like Linux is being considered like a security issue or something. Or is it like Facebook was saying that? I don't know.
Huh.
Have you
Okay.
heard of
I have not.
that? Okay.
Like, as a client or as a server?
I don't honestly don't know. I didn't even click
Yeah.
it. I just saw like some like clickbaity article saying like, oh, Linux is a security vulnerability according to Facebook. So I was like, oh, what else are they using then?
I mean,
Yeah.
Windows is not that much better. Or anything for them.
No, yeah. I mean, unless they want everyone to use a Mac.
I think Mac that's just what do you call it? Lack of exposure. If it was 90% of clients, then you're gonna get way more.
Mhm.
Yeah, I've been enjoying my Mac. I mean, just the Apple Silicon is really fantastic platform
Yeah.
in terms of like battery life and those kind of
Yep.
real world kind of things. You know,
Absolutely.
I'm actually still on like an Intel Mac.
yeah, the difference I think is significant in my opinion
Mm,
between that. Obviously, you have like compatibility issues with certain software and stuff, but if you're using, pretty modern or typical things, it's usually not an issue.
right, yeah.
Yeah, but
Especially it's been many years now.
the lock-in around the ecosystem also kind
Yeah,
of concerned me. It's insidious, but
definitely.
eventually you find everything
You're making a trade-off there for sure.
Yeah.
Mhm. Yeah, I've been getting pushed to trade up for one of the new ARM Mac machines, and haven't done it yet, but I've been noticing more and more projects starting to try and deprecate the old Intel Mac support. So
Mhm.
yeah, been thinking about it. Haven't actually pulled the trigger on that yet.
Yeah, unless you have like a software requirement, I think it's most definitely there's benefit. I'm assuming you were talking about work, so
Yeah. I'm not talking about work. I'm not.
yeah.
Yeah, I'm not using a Mac for like personal projects really.
I remember when they first rolled it out, it seemed like the Python world had a lot of problems. I think for performance reasons, a lot of their packages are C under the covers, and they started having problems getting it to run on the new CPUs. But
Right.
I'm not a Python guy, so
Oh
take
yeah,
that with a grain of salt.
that makes sense. I find like a lot of Rust projects also are kind of similar too. Like there's you require like some version of like GCC or like uh, glibc.
libc.
Yeah, and we've run into a lot of issues with libc, especially with packaging native components for our clients. So like we have a bunch of wrappers in like Java, Golang, Python, Node, for example, and they all wrap a Rust core, and we have a fancy build matrix and everything in CI to cut out builds for every platform under the sun, and then we run into problems because you have to be careful with like cross compilation, like
Mhm.
make sure you have like the right glibc version installed, or else everything goes to hell, and you can't figure out what's wrong, and kind of figure out like why is this complaining about this not being here.
Yeah, plus with a lot of like numerics or graphic stuff, a lot of Rust crates are really just FFI bindings to the reference.
I've noticed that, yeah.
Plus implementation.
Yeah, I know like Raylib is particularly beloved by many people, and so it kind of makes sense. Like, why would I, roll my own solution in language X when I could just, wrap Raylib kind of thing? So I kind of get that.
Yeah, I ran into it with a library called FFTW. It's Fast Fourier Transform, and I
okay.
think the C implementation, is sort of super highly optimized. It makes algorithmic decisions based on what kind of CPU it's running on and things like that. It would probably be a lot of work to replicate that in a rewrite.
Mhm.
Well, it says
Yeah.
it's written in OCaml as well as C, obviously.
Oh, really? What?
Yeah, I just looked up at your FFTW3, right?
Yeah. Oh, Camel.
Yeah.
Really?
Yeah. 13%. I don't know what 13%.
Oh, you're at the GitHub.
Yeah, I looked at the GitHub too, but
Yeah,
I was looking at the wiki page.
I mean, 13% is not
Yeah,
insignificant.
that's
Huh,
interesting.
I wonder why OCaml. That is very interesting. That's weird.
It probably started as a pet project, right? That's how a lot of these things.
I guess so.
Cool.
I think that's functional, right?
Yeah.
But that just strikes me as so bizarre.
I mean, is it really when you think about it? If you're a person really passionate about Fourier transform, you're really a math physics guy.
I guess.
Does it make sense for them to love functional languages?
I mean, I know a lot of like math people who just like
No, I'm just saying.
right? They just use Python, or I don't know. Not necessarily gonna like OCaml, but
I think
Well,
it depends,
this
right?
is a math person that wants to write some
oh,
library.
right.
That
Like,
loves fast Fourier transform, right?
yeah, okay. No, I know that person. I know someone who's he's actually a biochemist.
Yeah.
And he really likes Idris, and Idris is it's a dependently typed programming language, research language, and yeah, he basically forces everybody he works with to use Idris, and he writes Idris. He wrote I think he wrote like a package manager for Idris, and he's like, yeah, you're gonna use this as well, and that's kind of like the community package manager now, unofficially.
Is this Stefan?
Stefan? I can't remember if that's his name.
Is the package manager named Pack?
Yes.
Yeah, that's Stefan.
Wait, yes. Wait, do you know?
I don't know him personally. I've interacted with him on the
Yeah, I've talked to him a little bit too.
Discord server.
Oh, are you on the Idris Discord server too?
Yeah.
No way! I'm there too.
Idris is where it's at, man.
It is cool. I love Idris. It's neat. Not really like super practical to use right now, but I think it's fun.
I mean, I think that figuring out how to introduce dependent type, how to ergonomically make use of dependent types is definitely an interesting line of research in programming languages.
Yeah, definitely. Definitely there as well. Like that's kind of why I've been digging a little bit into ATS as well.
Mhm.
They seem to have figured out well, something that allows them to use dependent types in a more, I guess, practical setting. I know they've managed to at least beat C in the benchmarking games
Wow,
in some cases. So
interesting.
definitely interesting area of study. But I kind of looked at what they were doing, and it's different from what I expected. It's not quite like how Idris integrates dependent types into language into like one like uniform language. It's more like they have like 3 different types of data definitions in the ATS, and like you have your dynamic terms, which are the things that are, I guess, they're like the runtime stuff, the stuff that actually does the computation, and then all your proofs kind of exist at this compile time level, so they're like proof irrelevant. But yeah, they have like I think data values and data props to handle all that stuff, and then you can just layer that on top of some other kind of language. I think they said that their approach works for not even just functional languages, but you could like layer this system on top of like an object-oriented imperative programming language instead as well, and you get similar benefits. So yeah, it seems kind of neat, but also like a lot of extra syntax, a lot of extra machinery, boilerplate. So curious to see where that goes and how it compares to what Idris has been doing with QTT.
Yeah, I just discovered ATS myself. I don't know much about it. I'm watching my first talk right now.
Yeah, they said that it beat it on the benchmarking games, or it beat C on the benchmarking games, but the moderators of the benchmarking games had to remove ATS from leaderboards because they just couldn't verify the solutions. They're like, this language is too hard to understand, so we're just going to remove it.
Well, that's the other problem is we're seeing in the Linux kernel, C programmers tend to be these crufty old guys who really aren't interested in learning.
Oh yeah, I've been hearing about the I guess drama, the debacle, with, Rust and the Linux kernel. Yeah, definitely been coming up in my newsfeed quite a bit.
Yeah, I haven't followed it very closely, but
it feels like bike shedding to me because like that's I don't know. It is what it is. People have opinions. They have strong opinions on what belongs or doesn't belong in the Linux kernel. Linus Torvalds is Linus Torvalds.
I thought he'd mellowed in his old age.
I think this is his mellowed.
Yeah.
Yes, he used to be much worse.
I think it's a matter of time, right? Like,
maybe. I mean, we'll see. I mean, C has,
and I think a little bit of like there has to be proof in the pudding, right? Like, obviously that this is chicken and the egg a little bit, where you have to let it in and let it be used and mature a bit.
But when you've got NIST urging people not to use your language, I think it's time for a little self-reflection.
I feel like most languages sort of have like a lifespan to them. So we'll see what happens with Rust in the future. I mean, it looks pretty promising now, but who really knows? C has really withstood the test of time, I feel. There's been so many alternatives to C that people have created. I mean, there's like Zig now as well, and Odin, Jai. And, like nobody can really completely kill C. It's just they kind of just take bits and pieces of its community away from it. But
Well, and even if they do manage to kill it for new development, the legacy code base is vast and it tends to cluster in infrastructural places, right?
right, yeah. It's not like you can just wholesale rip out this stuff and be like, yeah, this is totally fine. If you try to, rewrite it in Rust or any other language, you're bound to run into bugs and breaking changes and stuff. So not a wise decision. by any means.
So
That's understandable.
Yeah, I think it's going to be interesting with the new lang. I mean, I think part of the problem with Zig, I'm just curious, like, what is going to be the thing that makes it so much better than C, other than ergonomics, right? Ergonomics are valuable. That's without a doubt. Everyone wants to write in an easier language, right?
Mm-hmm.
But like, what's the killer feature, right? I think Rust has, Rust does memory safety, but is as nearly as fast as C, right? Versus
Well-
all other kind of memory safety languages are generally a magnitude slower. Right.
Well, and having worked on the SRE side of the house at times, I can tell you a memory safe language without a runtime is huge, right?
Exactly.
We loved
Yeah.
operating Rust programs. They just kind of sat there quietly and did their jobs. No weird tail latency issues, no stop the world garbage collections. It just worked.
Right. Yeah. I mean, I guess Zig is being used in Bun, right? I don't know how I'd call that like it's killer.
I think that isn't that more just they didn't want to use C, so they use like
Zig
they just
is-
want to compile to LLVM, right? Like that's ultimately what they're trying to do, right?
Yeah.
I'm more talking from the adoption level. Like, why would I want to really use Zig beyond it just being a good alternative to C? And maybe that's sufficient, right? In the long term, but it's hard to say. Like Rust, at least there's like a big, like there's like glaring big feature, which is memory safety without GC, right?
Right.
And and performance, right? Which is like there. I don't think there's not many languages that do that, right? Very few, and definitely not ones that have gotten this popular, right?
Well, the way that I see it is that it's not dissimilar to Kotlin's position, where people
Yeah,
Kotlin is
that's
like a
fair.
better Java, right?
Yeah,
Zig is kind of like a quote unquote better C. So I feel like with the right funding, because let's face it, every popular language has funding.
yeah.
That I feel like it could be popular. I don't really see it getting there quite yet. Like I see, like it has some niche use cases. Like obviously it's used for cross compilation for Rust, and they're using it in Bun. But like I've kind of done a little bit of digging into Zig myself, and like a lot of libraries are just like not maintained, and they're like stuff like here's like a Postgres client, right? That's like this is the Zig
Mhm.
Postgres. It hasn't been updated in like 5 years or something. It's just
Yeah, the critical mass of
it makes you
developer
not feel
area,
like
yeah.
it's like it's not really there, and it's kind of languishing in its infancy.
I mean, it has to get like for a systems level language. I think it will have to get to 1.0 first, right?
Right? Yeah, exactly. It has to hit. It has to reach some kind of like critical mass before it sees real widespread adoption and use.
I watched a talk once given by one of the guys that worked to introduce Rust at Facebook. And he said that for it to work, a language can't be, like you were saying, 10% better. It's just there's too much inertia. People like the old ways. People don't want to change their development workflow, their tool chain, etc. There has to be like a killer feature that is going to really move the needle for that team in order to get them on board and willing to pay the switching costs.
Absolutely.
Yeah, that's why I'm kind of disappointed that Rust doesn't have dependent types, because I feel like now if anyone tries to do something like Rust,
It's stuck.
not
Yeah.
gonna fly. It's never gonna get off the ground.
Yeah.
All right.
Um,
Well, anyway, looks like we've got people kind of dropping out here, so we might just wrap things up here. So yeah, I just want to quickly thank everyone for showing up. I really appreciate it, because without people coming to the meetups, there is no meetup. So yeah, thank you all for showing up, participating, asking questions, chatting, and yeah, next time, I think we had a couple of talks lined up. We had one from Aaron Sealis. He's not here right now, but he's one of our regulars who comes for the in-persons usually. And I think Chester was also going to do a short talk as well. But
Do you remember what it was supposed to be on?
I don't remember what you were going to talk about.
No.
Oh my god. Okay, maybe
I
not.
remember it was something that I had to do anyway. That's all I remember.
Oh no. Okay, maybe it's just one talk potentially.
Oh, okay.
I don't
If you figure
remember.
it out, let me know. I can't remember.
I didn't note it down. If you remember it though, we can I guess proceed with that. No, wait, I remember now. Oh, it was bacon. You were going to talk about bacon.
Oh, I was gonna talk about bacon, right? Okay.
Yeah.
Yeah.
Okay.
The watcher, right?
Yeah.
Right.
Yeah.
Ball watcher. Yeah, so he was going to do a talk on bacon. Aaron was going to do a talk on performance benchmarking, I think, in Rust.
I think so. It was something that I wanted to hear about. But
Yeah,
does anybody do development on Windows? No, right?
I know one person who does.
Yeah.
But
Because I was getting some issues with bacon and ignoring files on Windows, and I was like, you know what? Just don't use bacon. Just run manually. I've had enough. But if I could repurpose to my machine, then I could probably file a bug. But I was like, nah, it's just not worth the effort. But yeah, I can definitely do a talk on bacon. I think bacon's pretty cool.
Okay, cool. Yeah, and I think if all goes well, we'll also have a talk from Aaron next month as well, which should be pretty interesting. I think he also said that he was going to be covering like how to do performance benchmarking when there's an FFI boundary involved as well, which is very relevant to my use cases at work. So hopefully that's the plan going forward. We're currently doing a partnership with Manning Publications right now, so plans are kind of tentative right now because they haven't gotten back to me yet. I need to follow up with them. They've been kind of dragging their feet on this. But, there we might be getting some talks from a couple of authors of some Rust books.
Cool.
Available on Manning. So yeah, other stuff to look forward to there. But yeah, that's pretty much it for today. So without further ado, unless anyone wants to talk about something else, I think this is where we're gonna cap things off. So,
Thank you for the talk.
And thanks for the talk. Yeah, it was pretty good.
thank you all for coming.
Thanks. Take care.
Take care.
All right, everybody. Thank you. Bye.